Well, it's a great pleasure to introduce Virginie Charette from the University of Sherbrooke. When Bill Goldman was here a year and a half ago, he said, by all means, you must invite Virginie Charette. And ta-da! Took a while to organize, but here she is.
Well, thank you. And you know who to blame now. Well, thank you very much. I want to thank Stephanie for inviting me and for the warm welcome. And I want to thank everybody here. So far, it's been really great to be here. So I'm going to talk about some symplectic geometry in the Einstein universe. Hopefully, I'll get to the symplectic geometry part, but I don't want to rush too much either. Start by saying this is joint work with Jean-Philippe Burel, Dominique Francard, and Bill Goldman. So I'm going to start with a little bit of motivation, why I'm interested in this problem. We're going to talk about the Einstein universe, what it is, talk about things that are called crooked surfaces. So I'm going to say what that is too. I'm then going to switch over to four-dimensional symplectic space and describe how the Einstein universe can be thought of what are called Lagrangian planes in four-dimensional symplectic vector space, and try to use some of that to prove some theorems, well, at least a lemma about the Einstein universe, about crooked surfaces in the Einstein universe. So that's the rough outline. So I'm going to start with some motivation, which I think I'm going to hide over here. So the reason that we got interested in the Einstein universe is that it's what we call the conformal compactification of Minkowski three-dimensional space-time, so 2 dimensions of space and 1 dimension of time. So the early motivation was the discovery of proper actions on R3 by free groups in the group of isometries of R21. So R21 is just R3 with a signature 2-1 dot product. So we're thinking x squared plus y squared minus z squared here. Okay? So let me just draw a cartoon picture of the kinds of groups that we're looking at. If we were looking in H2, if we're looking in the hyperbolic plane, for instance, what you would take is you would take 2 pairwise disjoint lines, pairwise disjoint geodesics, and you take a hyperbolic isometry that pairs this guy to this guy and actually takes this half plane and maps it to the exterior of this half plane. And if you take another pair of pairwise disjoint geodesics like this, then the group generated by G1 and G2 is a Schottky group. So sometimes we will call this ping pong dynamics or something like that. And because you can show that the group acts freely and it acts properly discontinuously on H2, just because everything has to move away from each other by this sort of ping pong that you're playing. And you get this kind of action as well on R3 because secretly the hyperbolic plane is lying inside of the Minkowski space-time by looking at the unit hyperboloid. So, but I don't want to get too much into that because that takes a real long time. We'll be reviewing some of these ideas when we get to the Einstein universe anyways. But basically, this yields proper actions on R21. And how we get these is you construct Schottky type fundamental domains bounded by things called crooked planes. Now, crooked planes are piecewise linear objects, and they were introduced by Todd Drum, actually in the late 80s, early 90s, to look at these kinds of actions. And again, well, I'll maybe just draw a very quick picture of what it actually looks like. So a crooked plane, it's got a piece that looks like this, but it's going down like this and down like this, so it lies in a plane. You've got these two light-like lines here, and you take the inside here and here. And this lies on a light cone, and what you do is you take a half plane here that's tangent to the light cone, and you take another half plane here that's tangent to the light cone. So this is sort of what crooked planes look like in R21. And if you're willing to believe me, these things, you can fold them up a lot, and so you can actually get them disjoint from each other, in the same way as you can get geodesics disjoint from each other in the hyperbolic plane. So you build these Schottky type actions on Minkowski space. And so this was really great, and we had a lot of fun with that. And then what we decided to do, well, how can we push this further? And one of the things that we were interested in is to look at the conformal compactification of R21. So Minkowski space-time is three-dimensional. R3, it's got a space-time structure. So you've got a notion of light cones. And the conformal compactification, one way to see it is simply you just plop up a time cone at infinity. And so you've got a cone here, and somehow you attach the future to the past in such a way that light travels along a circle. Okay, so that's a 30-second description of what the Einstein universe is, but we'll get a little bit more into it into the next section. But for now, you just think, I'm adding a light cone at infinity, and I'm closing up light geodesics. So light travels along circles. Okay, so that's the idea. And that's the motivation. And so now we can get, if I haven't forgotten anything, so now what I'm going to do, my Blackboard organization is kind of off, I realize that. So I'm going to start, now I'm going to talk about what the Einstein universe is. Okay, so, and it really is just conformal compactification of Minkowski spacetime. But we're going to do this in a little bit of a sneaky way. So what we do is we start with, so I'm going to take R32, and what that is, maybe I'll just define it this way. So I take five-dimensional real vector space, and I'm going to endow it with the signature 3-2 dot product, and let me just write it this way. I'm just going to write the quadratic form because it's easier. So I've got x1 squared plus x2 squared plus x3 squared minus x4, x5. And it's an exercise to show that this is signature 3-2. Okay, so it's 5 dimensions. That's pretty big for a 3-dimensional space, but we're going to reduce things a little bit. So we have in here, we have vectors that are whose dot product with themselves is 0. So there's a notion of a light cone. So what we're going to do is we're going to take n of R32, sorry, but I'm going to remove 0. So this is the light cone of R32, but minus a 0 vector. Okay, so imagine a 4-dimensional light cone, which is kind of hard. So we try to just think of something like this, right, in 3 dimensions. But it's just a set of vectors in R5 whose dot product with themselves is equal to 0. Okay, and you can think of all sorts of examples here. Actually, 1, 0, 0, 0, for instance, is a null vector, et cetera. Not 1, 0, 0, no, sorry. Well, 0, 0, 0, 1, 0 is a null vector, et cetera, et cetera. Okay, and so the next step is And this is how I'm going to define the Einstein universe. And I'm just going to denote it as Ein21. So I'm going to take this null cone, or this light cone, with the 0 vector removed, and I'm going to quotient out by scaling. Okay, so any null vector is going to be glued with any multiple of itself. Okay, so this is a kind of a...
You are quoting out by all, not just by positive scalars, but by
all
non-zero scalars.
Right, yeah. So, okay. Right, actually, if you mod it out by positive scalars, you'd get the double cover, which actually, this is good. Some people will call that the Einstein universe. This is harder, so I like it better. I don't know what the good, but yeah, this is good to point out. So I am going to be scaling out by all reals except 0. And so now it's just it's an exercise to see that if you take something with a 3-2 signature, you look at its light cone, the restriction of the dot product of the light cone is degenerate. However, scaling out removes that degeneracy, and you go down to a signature 2-1 dot product. And so this is something that does have a Lorentzian structure. So Ein21 has a, well, it has a, well, I should say a conformal Lorentzian structure, because there's something undetermined about this, because you are scaling. So, if you take a vector, you take a multiple, you're not going to get the same answer. So it's a conformally flat Lorentzian structure. Another way to see this, if I have an x in R21, I can map it to x. How do you do this? It's dot product 1 in Ein21. Well, you take the class under scalar multiplication. So this is so any vector in R21, this will map to something that's norm 0. Dot product with itself is 0. So you go into the null cone, and then you scale out by multiplication, and you're going to get so you can map R21 into Ein21, and you can use this map, and then you can use some sort of involuted version of this map to induce. So this endows. This is another way of endowing Ein21 with a conformal Lorentzian structure. And if this were a 2-hour talk, we would linger on this to see that, but instead I'll just leave it as an exercise, to see that the points that you're missing really do form a light cone in the Einstein universe. So you're missing a cone. Okay, so that's how you recover that picture of the Einstein universe just being a conformal compactification of Minkowski space height intervention 3. Okay, so basically you're missing all the guys who have a 0 here, and then you sort of work that out and you see how you get.
This map is injective, but not optical. That's what you're saying.
Yeah. Yeah. Yeah, you get everything except a light cone. Okay.
I'm a bit puzzled why you call it R32, because the X4X5 has a plus and a minus. Shouldn't it be R41?
No.
Is that minus x3 squared?
Yes.
Yeah.
You did change a minus sign in there. It's just inside joke. Sorry. Well, thank you. That is the strangest mistake for me to make, I have to say. But I've been teaching differential geometry this semester. That's my excuse. I've been careful all semester not to put any minus signs, and this is where it gets me. So, anyways, now I'm going to come back. Let you think, rethink everything now. Okay, so now we've got, so now we really do have something that's Lorentzian, and it's all good. So let's talk about this Einstein Universe a little bit. Let's spend some time getting to know it. So first of all, here's how I like to draw it. So it might not be obvious by using this form of the dot product, but really Einstein Universe, so I'll call this a fact. So Einstein Universe, it's homeomorphic or whatever you want to say. It's basically, it's an S2 times S1 modded out by the antipodal map. Which is the antipodal map on each factor. Okay? So, so you can think of a bracelet of spheres, and somehow you're gluing them together by the antipodal map, and so you're getting a weirder bracelet of spheres. And if you want to try to draw anything in here, which is what I like to do, I like to draw, well, you have to remove something. So to draw this, the first thing is we're going to remove a point in S1. So now we're just going to get a chain of spheres. And then the next thing that we're going to do, that's still too hard for me. I can't draw a chain of spheres. So what I'm going to do is the second thing is I'm going to remove a point in S2. So basically, on each of these spheres, I'm going to remove, let's just say, the North Pole or something. And I'm going to remove it everywhere. So really, I'm removing an S1. And so now what do I get? I get a chain of disks. This I can draw. So I get something like this. Okay, so here I've removed a point from the sphere. And here I've removed a point from the circle. Okay, so I'm going to draw everything like this. And so now we're going to, and I'm going to draw a few pictures of some of the characters that we meet in the Einstein universe. So some objects in R21. So, and I'm going to make this an even bigger picture here. Well, obviously there are points in R21. That wasn't too hard. Maybe the first really interesting object, there's something that we call photons. So actually photons are null lines in Einstein Universe. Okay, so they're null lines. And there's several different ways of introducing these. I mean, all of these objects, by the way, you can recover them by taking you take either a space-like vector or a time-like or a null vector in R32. You look at its orthogonal hyperplane, you intersect that with the Einstein universe, and you get all these objects. Okay, so photons, actually, you get it by taking the orthogonal to a null vector, shockingly enough. But what they look like is they look something like this. So what you get are, so this is glued together by the antipodal map, right? So this point is actually the same as this point that I removed here. So this is a photon. And these are circles. Well, they're closed curves in Einstein Universe. So remember when I said earlier that how you get the compactification is you add a light cone, but you close it up so that photons are closed, so closed curves. So we get something like this here as well. So since we do have a Lorentzian structure, so these are lines along which the tangent vector is a null vector. Its dot product with itself is 0. Okay, and actually, if no, I'm not going to give notation for that. So the next interesting object in R21, well, we have light cones, which I might sometimes call null cones, and there's no reason for that. So light cones actually, so here again, you're going to get, oh, maybe what I said earlier was wrong. So a null cone is you're going to take, I have to think about it. It's the intersection of an orthogonal plane with the light cone in R32. And what they're going to look like, actually, so they're going to be pinched tori. And what they're going to look like, they're going to start by looking like, in this picture it really looks like, well, it kind of looks like a regular light cone as we usually draw them. But again, this point is the same as the point that we removed here. So you see, torus, 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 and then pinch torus. Okay. And so if this is the point P, the notation I'm going to use, so this is pinch tori in Ein21. And the notation I'm going to use, I'm not going to use it very often, but I'm going to use it at least once, and I'll remind you what it means. But I'm just going to use LP for light cone at P. Okay, so these are nice objects. And so far, these objects don't really depend on the scaling. Since it's always some dot product equal to 0. Well, no matter what representative you use in the scaling class, you'll be fine. So this is all good. Okay, and the next object, there are several more, but maybe one more object of interest that I want to talk about are what we call Einstein tori. Okay, so these are bona fide tori. They're homeomorphic. An Einstein torus is homeomorphic to a torus. But the Einstein universe is non-orientable. So actually, there's a single connected component to the complement. So that's a little confusing, but we get over it very quickly. So Einstein tori. So these are tori in Ein21. And maybe I'll just mention that they're copies of Ein11. So instead of playing with R32, if you played with R22 and took its light cone and modded its light cone out by scaling, you'd get the Einstein two-dimensional universe. And Einstein tori are exactly that. Okay, so one more thing, and now this picture will be completely useless. So maybe a typical example. I'm trying to decide which one is going to be. I think I'll take this one. So here's a typical example. Of an Einstein torus. Okay, so you take the equator here, so it's mapped back to the equator by the antipodal map. Okay, so that closes up, and it closes up as a torus. Another very typical Einstein torus, I don't want to draw it, but imagine, take this great circle here on this sphere, take that times S1. Okay, so what we're going to see is a plane or a planar object. And that will close up to become a torus. And that's another example of an Einstein torus. So if you're keeping track, I wonder, okay, I'm going to draw another picture. So I'm going to try to draw what R21 looks like in here. And maybe mention in passing that's what's nice about this, this embedding of R21 to the Einstein universe is that all of the isometries of Minkowski spacetime, including all the affine isometries, so linear isometries as well as translations and things like that, these all map into P032. So into the group of conformal transformations of the Einstein universe. So it's a nice space to see all of the isometries of R21. But so what I'm going to try to draw here. So here's my Einstein universe where I've removed a few things, and I've got a point here which I'm going to suggestively call P infinity. And I'm going to remove I had this like a script L before, right? So I'm going to remove the light cone. So I'm going to remove the light cone that's based at P infinity. So I'm removing all this. What remains is, well, the embedded image under this mapping of R21. And so depending on how I've defined everything, the origin is going to be mapped here typically. So I like to call it P0. So the usual light cone that we think of, the future light cone comes up here, but it continues up here, but this will map to the past. I mean, somehow this is infinity, and then we somehow glue everything back here, and you're going to see what we usually think of as a light cone, but here it just appears as one object here, pinched, but somewhere else. This is the xy plane. This sphere here is the xy plane. And so what would appear, for instance, as if you were to take a tangent plane to the light cone, well, that is a tangent plane to a light cone, so that's a null plane in R21, and that corresponds to a light cone of a point at infinity. So if I take this point here, x, this is its light cone. And it's going to look, well, depending on how you're drawing everything, it looks like a cone here. But if you looked at its pre-image back in R21, what you would see is a plane that is tangent to the light cone at the origin. Okay, so that's how you recover a picture of Minkowski spacetime in here. And you can translate everything around. You can switch, there's an involution that maps P0 to P infinity. So that's how you get a Lorentzian structure in the neighborhood of P infinity. And you can play all these sorts of games and draw these neat pictures. So far, so good? I don't know if I'm doing okay for time. Let's assume that I am. So the next thing I want to talk about are crooked surfaces. And if at some point, or maybe I'll say when the explanation becomes irretrievably unclear, just the key thing to remember is these are objects that play the role of, well, circles in the Riemann sphere or of geodesics in the hyperbolic plane. So you use them to bound regions that give you ping pong dynamics. Okay, so what we want are things that act like circles. So we want things that act like this. Okay, and crooked surfaces do the job. So, we know enough about them that we can compute things with them. So that's really the take-home message about them. Now, if you know what a crooked plane is, crooked surface is just a conformal compactification of a crooked plane. But if you don't know what a crooked plane is, well, we'll discuss what a crooked surface is. And the data for a crooked surface is as follows. So you do it in two steps. You start by pick 2 points. And I'm going to, for now, suggestively call them P0 and P infinity. Okay. And I'm going to take them, so I did not define this before, so non-incident. And what I mean by that, they do not lie on a common photon. Now, what that means is that if you took two of their representatives in R32, so you've got two vectors on the light cone, but their dot product is non-zero. When their dot product is 0, the 2 points span a photon in the Einstein universe, and if it's non-zero, then they don't span a photon. So we call them, when they're both on a photon, we call them incident. And so non-incident is that they're not. Okay, so we really want two guys that look like these two here. And when that happens, when they don't lie on a common photon, that means that their light cones intersect in a circle, which is not a photon. It's a space-like circle, but it looks like something like the circle, well, the circle that I drew here. So now pick 2 points. And I guess I'm going to call those Q1 and Q2. And these are both going to lie on the intersection of the light cone at P0 with the light cone at P infinity. Okay, so if I draw the picture here, so I've got P0 here, I've got P infinity here, I've got light cone, intersection, and maybe I'm going to pick these two. Okay, so I'm going to denote this by CS P0, P infinity, Q1, Q2. And that's going to be equal to, there's going to be a stem determined by P0 and P infinity. So basically what I'm going to do is I'm going to take the set of all points such that, that lie here or here and that are time-like with respect to that. I could say this in a much more technical way, but it amounts to looking at things like this. So basically what I'm doing is I'm taking the Einstein torus that is determined by these 4 points, and I'm taking points on that Einstein torus that lie on a time-like line from P0 to P infinity. And so I'm going to get, these look separated, but remember they're glued together. Okay? And then I'm going to take the union with, I'm going to take a wing which is a half light cone, and another wing, which is another half light cone. So this is a half light cone. And that's another. So I'm being extremely non-technical about this. But basically, I have to pick one. There are two. You see these two. There are these photons that are determined by this data. Actually, the 4 points yield these 4 photons. And so the photons bound to this pair of photons bounds to half-light cones. I pick one. And then on the other side, I pick the other, but I don't want them to be, I only want them to be intersect here. So they look kind of funky, these crooked surfaces, but I promise you that they work really well. I mean, this one looks like it's huge, and how could I possibly find another that, that is disjoint from it? But actually, you do. It's actually pretty easy to get them disjoint from each other. Okay, so I have a half light cone here. I've got a half light cone here. And I basically have 2 quadrants here of an Einstein torus. Okay? And actually here, it's also useful to think of this crooked surface as being given not only by these 4 points, but in a sort of a dual way. We can think of it as being given by these 4 photons. So basically, I have this pair of photons here, which don't meet in a point. And I've got another pair of photons here who do not meet in a point. But this one meets this one, and this one meets this one. So I've got these two crisscrosses, and I fit it all together. And that's another way to recover a crooked surface. Okay. Basically, what you want is you want these 4 photons to determine an Einstein torus. That's the basic rule of this game. Okay. So that's what a crooked surface looks like. But you can get the picture to look more like something like this. So this is the easiest one to draw, but it's, in a way, it's not that, well, they're not that typical. They look something like this. This is an extremely cartoon version of a crooked surface. And so I can get another one. And I can get a disjoint from the first. And once you know how to do this, okay, this doesn't look very believable. You can get a third one in there, and then you can plop a fourth one, and you can get them all disjoint. And you can get them to wrap around each other so that they're disjoint. Actually, there's a paper that I wrote with Francoeur and another graduate student, Rosemond Laroux-Dussault, where we explain how to construct these kinds of examples. So it's really easy to get these kinds of configurations. And so you get these pairings. So you can take an element of O32 that pairs this guy to this guy, and then this guy to the fourth one that I've refused to draw. And this yields.
Is it true that some elements, some isometries of R21 act with kind of north-south dynamics on this object? Or do you not get the picture?
You get something. It's not exactly north-south. There's some complications. But actually, in this case, you get something just as good. You get what Frances calls Lorentzian-Kleinian groups, which I want to say is the next best thing. But there's some, it's not obvious. But you do get something that's just as good, but it's not immediate. Okay? And so you get this kind of ping pong dynamics anyways. And so you construct these really nice actions. Actually, Frances studied these a lot, and he was really behind our motivation to start looking at the Einstein universe, because he was the first to think of conformal compactification of Minkowski spacetime and of these crooked planes. And so We just pushed it further. But he originated a lot of this work here. So these are what crooked surfaces kind of look like. And I have 10 minutes to talk about the relation to the symplectic space. I think I can do it. But so far, any other questions? So far, so good? Or it's as good as it's going to get? Okay, so where am I? If you're really curious, after the talk, I can show you pictures of crooked surfaces. I've drawn them. I've drawn some in Mathematica, and they tend to be really huge files, so it takes a really long time to render the picture and everything. Okay, so the next item we talk about is symplectic space. So symplectic R4. Okay, so I'm going to do this as basically as possible. So I'm actually going to start with the basis. So I'm going to call my basis E1 through E4, and I'm going to define omega as follows. I want omega of E1, E3 to be the same as omega of E2, E4 to be equal to 1. Antisymmetric. And all others are 0. So what that means is that in matrix form, the matrix for omega in this basis is I have a little 2 by 2 identity matrix here, and I have minus the identity here, and I have a 0 here. Okay, so this is a symplectic. Product. Okay, so the reason that's interesting is that we can use this to endow. Okay, it might look a little bit like I'm pulling it out of a hat. I realize it, but so what we're going to do is we're going to endow. We're going to take the exterior 2 product of R4 with a dot product. And how we're going to do this is if I have alpha and beta, which are in the exterior 2 product, if I take their wedge, that gives me some multiple of this guy. And what that multiple is going to be half the dot product, minus 1/2 the dot product. So the minus 1/2 obviously is there for some sort of mysterious normalization reason, which I'm not going to get into. I can't change it because otherwise I'm going to get confused. So I have to put that there, but it kind of makes sense. Okay, so we've got this dot product here, and it turns out that dot product is signature 3-2. And so 3-3, yes, yeah, that one is 3-3. And then, right, but what we're going to do is we're going to take, so set, I'm going to call omega star is going to be 1/2 this guy, and right, and its perp has signature 3-2. And I'm going to take the light cone of that. So that's the Einstein universe. But in this context, it's known as something else. It's the space of Lagrangian planes. Okay, so I'm going to call that lag R4. So what is a Lagrangian plane? So if I take so if I've got two vectors v and w such that where omega of vw is equal to 0, well, so this guy is a Lagrangian plane. Okay? So magically, well, not magically, after a lot of work, we get that Lagrangian planes in symplectic R4 are the same as the Einstein universe. And that's really nice because the Einstein universe, I love it, can't live without it, but it's not really easy to work with. So these crooked surfaces, how do you tell if two crooked surfaces are disjoint? Well, it involves usually a lot of really, really highly non-pretty calculations. I mean, I have some ways to make sure that they're disjoint, but if you give me two and you ask me, are they disjoint? I'll say, I don't know. So the only thing I can do is draw it and have Mathematica cry at me for a while. So it's really not easy if you're looking for any kind of explicit way to figure if two of these guys are disjoint. But now that we have this, you see, it comes with this omega. And I can use this form to my advantage. And I suspect I will only have time to illustrate this, yes, with one example, but hopefully it will convince you. So I'm coming over here. I'm going to call this an application. Okay? So what I'm going to do, I'm drawing the Einstein universe again, but now I'm going to use this stuff with Lagrangians. And now there's a dictionary. I won't write it down, but I will say it. There's a dictionary. Points in the Einstein universe correspond to Lagrangian planes. Now, if 2 points are incident, so they span a photon, that means that their corresponding Lagrangian planes intersect in a line. So lines in R4 correspond to photons in the Einstein universe. So questions about incidence, questions about photons in the Einstein universe amount to checking whether omega of something is 0. Okay, so that's going to be key in some of these things. So recall how I've decided what omega did. And now what I'm going to do is I'm going to draw some lines here. I'm going to draw some photons. And I might actually cheat and look at my notes. Okay, so there's a little bit of arbitrariness in here, but not that much. Okay, I've got E1 and E2. Omega of E1 and E2 is 0. So they lie on a common light cone, which corresponds to this plane, E1 wedge E2. Okay? And in the same way, I have, what order did I put this in? E3 and E4. And they also lie on a common light cone, which is E3 wedge E4. I have another one here, E1 wedge E4, and I have another one here, E2 wedge E3. Okay? E1 wedge E3 is non-zero, so they don't intersect. These photons do not intersect. And the same goes for E2 and E4. Okay, so each of these guys correspond to photons, because lines go to photons. Okay, and I'm going to give you a lemma. So a photon, so let Z, be a photon then Z is disjoint from the crooked surface determined by these four guys, E1, E2, E3, E4, if and only if two things. The first is that if I take omega of Z with, I'm cheating, E1 and E4, no, E3. What? This needs to be positive, and the other guy has to be negative. And the idea, so now I'm just going to say things, and I'm going to try to make it very quick. The idea being that the first thing to realize is that a photon can't just intersect the stem. It has to intersect one of the two half-light cones. So it's really a matter of checking that it doesn't intersect any of the two half-light cones. This guy, for instance, is positive linear combinations of E1 and E4. You can say, what do you mean by positive? I'll say, okay, make them both negative then. But you have this sort of positive linear combination here. And so not hitting this one is making sure that the dot product of Z with this combination of E1 and E4 can't be 0. But if this is positive and this is positive, the sign never changes. Same goes for the other side. It's negative, but the combinations, the components are negative too. So you get that. And in the end, you put this all together, you get this really explicit criterion for two crooked surfaces to be disjoint. Basically, you need to take the 4 photons of the first crooked surface, check that none of those photons hits the second, and vice versa. Okay, 16 inequalities to check, but it's still, it could be so much worse. And on that note, I want to thank you for your attention.
Are there any questions?
So you looked at a compactification of R21 by looking at a homogeneous space for SO23. Can you do that for any other PQs or any?
Yeah.
There's a general procedure.
Yeah,
for
yeah,
any-
yeah. I think the only question is how do you interpret it. But yeah, you can play this game with a lot of different spaces and see what happens.
For like, if you go to like conformal compactified or PQ, there's a homogeneous space of some
Yeah,
SONM that does that.
yeah, yeah. And it's fun. Yeah, if you're into that kind of stuff.
Any other questions? Well, if not, let's thank Virginie Charette again for